Hello there. So this is the video that I mentioned in class today that I would prepare to finish up chapter 13 so that we can move on in class on Friday in order to start chapter 14. The remaining material that we have in chapter 14 is a theoretical look at how factors like concentration and temperature and surface area and catalyst, how those play a role in affecting the rate of a chemical reaction. And this is all described under what we refer to as the collision theory. And so the collision theory, I've already got the text written up here, so if I'm going a little bit too fast, feel free to pause as you're watching and make sure you write all this down into your notes. But the collision theory is pretty straightforward. I think when we look at it in hindsight after I go through it, you'll say, yeah, that makes a lot of sense. So in order for a reaction to occur successfully, three conditions must be met. If we cannot achieve these three items here, we're not actually going to have a chemical reaction occur. Right? And the first is where the name comes from. The reacting particles must collide with one another. So I brought in a couple of molecules to serve as a visual aid. If I want, for example, to transfer the white ball here, let's say this is going to be a hydrogen. This will be the type of reaction that we'll look at in a couple of chapters actually. Let's say we want to transfer the hydrogen from this molecule to this molecule here. We actually need these two things to physically come into contact at some point in time if we're going to achieve that outcome. All right? So that's rule number one, or idea number one. They have to collide. But every collision of these two molecules isn't going to lead to a successful reaction, as it turns out. Because this hydrogen right now is held onto by its current owner, the molecule here. And it's not going to give it away for free. So if our new molecule is going to take possession of the hydrogen, the collision has to occur with enough energy so that we can actually break off the rest of the original molecule, and then we see physically transfer our hydrogen atom over to its new molecule. And it's energy, or the speed at which these things collide, that's going to allow this to happen here. All right? So that ought to be planting a seed in your mind right now. Temperature's got to play a role then, because temperature is how we basically get our energy or measure our energy in a chemical system, right? And so that's going to definitely be an important factor. And then the third condition that we have to achieve is how physically these two molecules interact with each other. I've color coordinated my molecules a little bit. You see I'm transferring the hydrogen from the red to the blue, if that's where it needs to land. So I can't have the other red colliding with it, or this gray part colliding with it, or one of these black parts. They're not the right part of this new molecule to physically take ownership of the hydrogen. So the orientation, physically how these two run into each other, is a crucial piece of this puzzle, so to speak, as well. And we have to have all three conditions. They've got to meet with enough energy, and they have to meet in the right orientation. And we can control the success of these outcomes, all right, or how often we achieve them with some of the variables that I mentioned earlier. The more often we're able to achieve these three outcomes, the faster our chemical reaction is going to occur. All right, now let's go in and add a few little tidbits here and there. This with enough energy, we have a name specifically for the amount of energy that every reaction requires in order to occur. It's called the activation energy. We use EA as its symbol. It's the minimum energy required for a reaction to occur. If you don't have that energy in your molecules, when they collide, it's just simply not going to be enough to accomplish the transfer or the breaking of the bonds. And so the activation energy is a pretty crucial piece of information. As far as the orientation goes, we often use what's called the frequency factor. The frequency factor is A, right? And it basically is equivalent to the percentage of possible collisions with the correct orientation. Okay? I won't use those two molecules, but imagine this could be, these two pens could be a simple case as well. Imagine that the green marker is going to transfer its cap to the back end of the black marker, like I've just done there. That's the only possible orientation that allows this to occur. If the green marker comes in and bumps in this orientation, we are not going to have a successful reaction. So having one out of all the different possible ways these two things could, hit, you see it's a pretty small percentage. And for many reactions, that's going to be the case. And not that we'll figure out a way around that later on, but I'll show you how chemically we seem to overcome a very small frequency factor. Okay. Now, the idea of activation energy and frequency factor, they are combined in an equation that helps us predict or calculate what any reaction's rate constant should be. Okay. This equation is known as the Arrhenius Equation. The rate constant K of a reaction is equal to the frequency factor times E raised to the negative E sub A divided by R and T. Right? Now, R is our ideal gas constant. We've used it a couple of times this semester. In this case, again, notice where R is in relation to another term that is an energy. E sub A I just defined as an energy. And so R is going to be in its energy unit set, 8.314 joules per mole Kelvin. A, I've just defined as the frequency factor. It would be a constant for a given reaction. Probably you'd be able to look it up. Maybe you'd be doing an experiment to try to figure it out. All right. T, of course, would be the temperature, which needs to be in Kelvin. And then E sub A is the activation energy, as I just described it. Okay. So this equation would allow you to figure out any reaction's activation energy. Now, the lab that we did this week studying the rate of the crystal violet experiment, we did it at two different temperatures so that we could actually find the activation energy. Right? If you remember, a little while ago, we studied vapor pressure and the Clausius-Clapeyron equation. The Clausius-Clapeyron equation was ln of P equals negative delta H over RT plus some constant. All right? This would predict the vapor pressure at any temperature, and ultimately we turned this into a two-point version that in lab we used to predict the boiling point of water. We can similarly do something with this equation as well. We can linearize this exponential equation, and it takes on a form that the ln of the reaction's rate constant at a second temperature divided by the rate constant at a first temperature is equal to E sub A divided by R times 1 over T2 minus 1 over T1. Okay. And so if we have 2 points, we can use, two rate constants to find the activation energy. So in lab, we actually generated several different rate constants, so you're working on that right now while I'm away. and you should be able to find the activation energy for the crystal violet reaction. So this is just for 2 points. You could also have an entire graph where you plot the ln of several K values versus 1 over temperatures. Very similar to what we did back here with our Clausius-Clapeyron equation, right? So we're using the same tools, the same techniques to solve multiple different problems. And that's why these mathematical skills are so fundamental to our work as chemists, right? But a graph of this would roughly be a straight line. And if you added your trend line to it, okay, the generic form of this straight line, of course, is always y equals mx plus b. But for the linearized version here, it would be ln of k, that's our y variables, equals negative e sub a over r times 1 over t plus a constant. This constant would actually be the ln of your frequency factor. But importantly, since x is our 1 over temperature values and y are the ln of k values, the slope of this line right here is negative e sub a over r. So if you have multiple data points, you would find the e sub a activation energy by taking the slope of your graph times negative r. And that would give you the activation energy in joules per mole. These are joules per mole Kelvin. Sorry, I'll fix that little typo there. So these are a couple of things about this. All right, welcome back. The video cut off a pretty good point, actually. I had just finished going over how we use the Arrhenius equation to find the activation energy. That's going to be relevant to what we do in lab. I want to extend a little bit further now on the uses of the Arrhenius equation. So I've rewritten the 2-point version of it. So when we know 2 rate constants and their accompanying temperatures, for example, or actually if we don't know both rate constants and both temperatures, that's what we can use the equation to do. So what I've shown here first is the manipulation if we want to solve for the rate constant K at some temperature. So we're in the lab and we've performed an experiment, for example, and we know the rate constant at 1 temperature. We can use this equation to predict what the new rate constant would be at a different temperature, T2. Now, so we would solve all of this with the 2 temperatures, turn all that into a number, and then that would become the exponent, our e to the x. All right? Our other option would be to solve for what temperature would we need, okay, to maybe heat up or cool a reaction to in order to accomplish a particular rate constant. This might look pretty familiar. This is a lot like your equation to solve for the temperature to accomplish a certain vapor pressure. It's really the same formula, same stuff happening here, except now we've got rate constants in their relations to temperatures and activation energy instead of vapor pressures. That's what we have in the Clausius-Clapeyron equation relative to the enthalpy of vaporization. Right? So you may find yourself needing to use these manipulations of the Arrhenius equation in your homework. Okay? Now another helpful way to understand the role of temperature in dictating the rate of a chemical reaction is to remember that in a collection of molecules, all right, your molecules are distributed over all the possible energies. And so this y-axis would be the number of molecules having any particular energy. Now remember, we looked at this first in gases back in chapter 5, and the average temperature is what dictates the average energy, sorry, is what dictates the temperature. What would be new now to consider is this activation energy. So somewhere along the x-axis would be, what is the activation energy of your reaction? Okay? Only particles that are at that energy or higher are going to be able to react. So it's this small set of particles that are capable of reacting. If we, however, change the temperature of our reaction, that redistributes our molecules like this. Now we have a much larger fraction of our molecules because we've pushed so many more above the activation energy. All right? So here we have a larger number that are able to react, which means it's going to be a faster reaction at that higher temperature. So the blue here would represent temperature 2, the black temperature 1, and temperature 2 is greater than temperature 1. Therefore, you have the faster reaction at temperature 2. So that's borne out sort of conceptually by considering where the activation energy is. But again, it's reinforced in the actual Arrhenius equation that we have over here. All right, what are some other things to consider about this collision theory? So in all the possible things that can happen in chemistry, it turns out that very few actually are reactions that involve just two simple little particles colliding. So, consider two atoms that might have to collide with each other. And they're going to bond together, right, to form the product. It really wouldn't matter what angle these two atoms bump into each other. They're both spheres, so they're always presenting the same sort of amount of surface contact to each other, right? And it's highly likely to be a successful collision from the orientation parameter that we considered. So this type of collision has a high value of A, the frequency factor. Okay? But what if we had, on the other hand, a much more complex situation where we had sort of an opening in a molecule, all right, and our other molecule like that. And you see that, I'm intentionally drawing these to be silly shapes. This fits into here. There are a lot of different ways that this molecule could accidentally collide with the first one over here, right? And this has a very small percentage of actually having this collide directly into the opening that's built for it. And so a reaction scenario like this would have a much smaller frequency factor A associated with it. And that would tend to lead to this being a slower reaction. So the more complex the shape of our molecules become, the odds tell us that the slower their reaction should be. So in the grand scheme of things, reactions involving atoms or very simply shaped molecules tend to be a lot faster than reactions involving large, complicated reactions. Now that said, reactions involving big molecules happen all the time. And we as human beings are living proof of that because we are full of big complex molecules, proteins, right? Amino acids, all these different chemicals that make up our DNA, that are flowing through us, that are part of our food and are getting digested. These are big molecules. And yet they're part of pretty fast reactions in most cases. So chemists struggled with, how do these big molecules, complicated shapes, how do they react in a pretty quick time frame, as it turns out? And our explanation of this is what we call mechanisms, or mechanism theory. Mechanism theory proposes that large reactions involving complex molecules and or multiple molecules okay, occur in a series of small reactions, okay? One or two particles at a time. Okay? These small reactions, another name for them is elementary reactions. Okay? And so we envision that a large reaction occurs not in one concerted collision of 5 or 6 different molecules at once, which would be nearly statistically impossible to think about getting 5 different molecules to crash together with the right amount of energy at the right moment in time, everything lined up perfectly to bond together. It's just physically not likely to happen. So rather than that, we imagine that a series of small, easily accomplished reactions can occur. Let's look at just a simple case. Even a reaction like 2 A's plus a B to form a C is unlikely to occur in one step, one stage, because getting the 3 molecules to come together at one moment in time is going to be very difficult. What's more likely to happen would be perhaps A plus B first come together and they form a temporary product. I'll just call it T. That T then collides with the second A and that produces C. If you balance this out like we did with Hess's law, you see that we've accomplished the 2 A's plus B giving us C. Now, a different way this could happen might be maybe A plus A produce that temporary product, and then the temporary product reacts with B to produce C. That's again going to lead to 2 A's plus B giving us C. So there's some ambiguity. Which way does it happen? How do we know? Kinetics is our tool to help us understand which pathway brings us to the actual overall outcome of this reaction, as it turns out. Okay? I'm going to pause right here, check that everything's working with the video, and then I'll resume in just a minute. All right, so we're ready to consider how does kinetics help us understand the mechanistic pathway, the series of small steps that occur in order to bring about a larger overall reaction. So I've cleared off my board, as you can see, got it reset, although these were the 2 proposed mechanisms that I had. Now, what I haven't yet explained, a couple little things here. What is T? This thing T is what we call an intermediate product. It's not something we would add to the process, not something we would ever actually pour into a chemical reaction. As you can see, it's just something that the reaction has made on its own in either case. So I've held it the same, although that would unlikely be the case, but I've called it T generically for temporary or intermediate product in each case. All right? And seldom are the intermediates anything that you could actually recover out of a chemical reaction. They're more like just conceptually there. They're often very short-lived, very reactive, so that as soon as it gets made, it can be consumed. The next thing that we need to do to get to our ultimate outcome here for our kinetic understanding is to know that an elementary reaction, like these 4 that I have written up here, so an elementary reaction has a rate law whose orders equal the reaction coefficients. Alright? It's a little thing we've come to understand about these elementary steps. This reaction of a molecule of A plus a molecule of B cannot happen unless you have an A and a B. So the rate of this first step is linearly, directly dependent on both A and B. I can't assume that down here in the 2A plus B to give me C. But for an elementary reaction where you have only one or two particles, you can, because you can't have the reaction without both A and B, or T and A. So the second equation would have a rate law, K2 times the concentration of T times the concentration of A. Now over here, we would have rate of the first step equaling K1 times A squared, because you would need two A's to collide to each other. So the success of that reaction depends on, and the rate depends on how many A's you have. The second step would be rate 2 equals K2 times T times B. All right, so we've been able to write individual rate laws for each of the steps. And here comes the clincher now. One step in the mechanism will be slower than all others. This step is called the rate determining step. And its rate law becomes or gives the rate law for the overall reaction. Okay? So if we can figure out which step in a particular mechanism is the slowest, that's going to tell us a lot about the overall reaction. Okay? Give you a little analogy. I was on my trip to Costa Rica recently, right? And each day our group would have to pack up out of our hotel and get onto our bus that would take us to our activity for the day, our hike for that day or our tour that we were doing. And there was always, in one of our groups, two students who were the slowest, right? They were the last people to get on the bus every single time. So no matter how fast I was or how fast most of my other students were, we always waited on the slowest people. A chemical reaction is the exact same way. No matter how fast most of your steps are, the whole process cannot be any faster than the slowest of your steps. So what we need to know is which are the slow steps. So what if I said this was the slow step in my first mechanism, or this was the slow step in my second mechanism? If that was the case, and I want to keep the mechanism, so I'm going to go ahead and erase down here. But if that was the case, then the rate law for that step becomes the overall rate law, although we would change the overall rate law for 2A plus B then would equal a now one just rate constant K times A times B. So we see that it's first order with respect to A and B. In this second proposed mechanism, the overall rate law, if this was the slow step, would be K times A squared. So we see that it's first order with respect to A, but zero order with respect to B. So what does that mean? Well, now we have to turn things around. In lab, we found the overall rate law for our crystal violet reaction. So if this was our proposed reaction, we could, just like we did in the lab, we could find the overall rate law. Let's say we did an experiment and we found this to be the overall rate law, that it was first order with respect to A and B. Working backwards then, that proves or tells us that somewhere in the process, A must collide with B in a step like this, okay? It might not mean that everything else is correct, all right? But it would mean that A collides with B at some point in the process. Conversely, if we find the rate law and overall we find that the rate law is A squared, all right, that would tell us that this is the mechanism that's correct, because this is the one that proposes one A has to bump into another unit of A. So knowing the rate law tells us a little bit about what collisions are occurring in the series of small steps that bring about an overall reaction. Okay? Let's do some more with these mechanisms here. I'll go ahead and erase the board, clear us off, and get us started with a clean slate in a minute. So we're ready to practice with another mechanism here, and I've got a few questions to accompany a theoretical mechanism that we're going to look at and learn a little bit more about these kinetics issues. So let's consider this mechanism. We've got 3 steps now. A plus B will produce C. C plus A in our second step will produce D, and then D will break apart into E and F. 3 pretty straightforward questions that might accompany a lot of mechanisms. What's the overall reaction being described? What is or are the intermediates, the intermediate products, if there are any? And then, can you use this to determine the overall reaction's rate law, the rate law of the overall reaction? Okay. But even if the first question wasn't asked, it's what we always need to do. So we just would sum up our reactions, sort of like Hess's law, looking for any cancellation across our arrows. And so you can see that the C produced in the first reaction is eliminated or used in the second reaction. The D produced in the second reaction is eliminated in the third. So your overall reaction becomes 2A plus a unit of B produces, in this case, E plus F. So that's the answer to our first question. Now what about the intermediates? The intermediates are anything that we've crossed out in that cancellation process, although I haven't yet talked about catalysts, and they'll be something we cross out as well. So I'll give you another mechanism in a minute for the catalyst. But in this case, that would be C and D. So our overall reaction, 2A plus B, give us E plus F. C and D are our intermediates. And now what's the rate law of the overall equation? Well, what I was saying in the previous segment was the rate law comes from the slowest step. And you notice I have written here that the second step is the slowest. So let's write the rate law for it. Rate for the second step would equal K2 times the concentration of C times the concentration of A. So that looks like it should be our answer. All right? So the rate equals K times C times A. At first glance, doesn't seem to be a problem. But there's a big problem with that. How can the rate of this reaction, ignore the mechanism for a second, how can the rate of this reaction involving chemicals A, B, E, and F, how can the speed of that depend on the amount of C that you have present? C is not a chemical that you have present. C is an internal part of this process. And so this is an invalid rate law because of the intermediate. So we have to get rid of the intermediate. And there's a sneaky little trick to that. Now remember, this step being the slowest, what it's probably going to mean is that this first step up here ends up being reversible. As A and B's react to form C, and the C's sort of wait around to react with additional A's, One possibility is that they might reverse and go backwards to A and B. So for my first reaction, I'm out of room up there, the forward rate law would be K1 forward times A and B. The reverse rate law, rate 1 reverse, would equal K1 reverse times the concentration of C. Because this is reversible, these two will equal one another at some point. These two reactions will reach an equilibrium, which we'll talk about in a lot more detail in the next chapter. Okay? And anyway, these two rates would equal each other. So K1 forward, A times B equals K1 reverse times C. Look at that. We can solve now for the concentration of C. The concentration of C equals, we're just going to call it K1 prime, although it would be K1 forward divided by K1 reverse times A and times B. What that lets us do is now substitute over here for the C. And so our overall rate law becomes rate equals, again, all the K's would get combined. The K1 forward, the K1 reverse, the K2 from this one. They'd all get combined into the overall rate constant times A and B, which originally came from C, times another A. So this reaction is A squared B. So it relies on all of those collisions, all three of them, although not all at once, happening. This becomes the overall rate law of this reaction. Okay. So, sneaky little thing we can do when an intermediate ends up in the rate law of a reaction. One more mechanism I want to show you would include a catalyst. So let's look at a case. How does a catalyst look different from an intermediate product? So consider this mechanism, again generically using letters like A and B. A plus B to produce N. B plus X to produce Q. N plus A to produce T. T plus Q to produce X plus Z. Right? Let's ask similar questions to what we did last time, although we won't worry about the overall rate law this time. Let's just go with what's the overall reaction, what are the intermediates, what is or are the catalysts. Okay. Now, so add things up. I see N would cancel with N. Q would cancel with Q. T would cancel with T. And X would cancel with X. All those things will cancel out. What do I have? 2 A's plus 2 B's producing just Z. So that's my overall reaction in this case. 2 A's plus 2B producing Z. You see, it's highly unlikely that you're going to get those 4 particles to collide all together in one big, concentrated collision. More likely that it's going to occur through a series of these simple steps like this. Now, everything we've crossed out is an answer to our next 2 questions. The difference is the perspective. Intermediate products are products first, reactants second. Catalysts are reactants first, products second. What do I mean by that? So N, the first time we see N, as we read our mechanism from top to bottom, it's a product. Then later on, N is a reactant, and it's the second time it shows up. That makes N an intermediate product. Q is the same way. reading from top to bottom and left to right. The first time you see Q is over here on the product side. Then later on, it cancels out down here. You know, you can almost do it this way. If you can draw a downhill arrow from right to left, that's going to be an intermediate product. That's going to be N, it's going to be Q, and that's going to be T. All three of them are intermediate products. But X is a downhill arrow from left to right. The first time we see X is as a reactant. If you're going to make step 2 happen, you have to add X to make it happen. Later on, the chemical system reforms and reproduces the X, which causes its cancellation in the overall reaction. So that's the definition of a catalyst there. All right? Now, in a minute, I'm going to pause again here. In a minute, I'll explain how a catalyst really changes the mechanism and how it makes a reaction go faster. And that'll wrap up the chapter for us. Okay, we're down to the home stretch here. The last thing we really need to consider is how does a catalyst do its job? And its job is to speed up a chemical reaction. And what it does is in that mechanism, that series of small steps that we were just looking at, is it causes the steps or one of the steps to have a lower activation energy than was the case if the catalyst was not there. So I drew out one of these distribution curves again, and like we saw earlier, what the catalyst would do is it would change the activation energy to a lower value. And then you can see that now all of these additional molecules, particularly this double shaded region here, are now capable of reacting. Sure, all of the original ones that met the original uncatalyzed activation energy are fine, but we've got this much larger chunk of molecules now, and so we're going to get a faster reaction as a result. A different way of understanding what's happening here would be to use another diagram that we frequently like to invoke, which is called a reaction coordinate diagram. A reaction coordinate diagram shows the energy, okay, during the progress of a reaction. Not quite the same thing as time, but rather internally what's happening during the reaction. All right? And so a reaction coordinate diagram would show, all right, if we have our two molecules, let's say we've got circle, circle, and then we've got a square over here. But what we're going to end up with is the circle, circle is going to break. We're going to break this bond and allow one of the circles to bond to the square. So how are we going to get from here to here? A good way to think about this is imagine drawing a whole bunch of pictures that represent these molecules moving. Kind of like a cartoon, an old-fashioned cartoon. You would have drawn out maybe a person, and then you would have drawn their arm moving a little bit, and then drawn them again. And you'd stack up all the pages, and you'd flip through those pages, and you would see the person move, right? That's how we used to make cartoons. So we could do that for a chemical reaction. This one, it would involve first having these molecules move closer to each other. Then there would be a stage where our two circles would start to stretch apart as the second circle begins to form its bond to the square. And then we would finally be successful in breaking that bond. So we'd have our circle and now our circle square put together. And then they would move apart to this. Okay? So all we would need to do then is figure out what's the energy at each stage. And so a typical reaction coordinate diagram might look something like this. All right? And this would be the energy at our first stage of our reactants. Okay, sorry about that. The camera shut off when the memory card filled up, so I've had to clear it off and get restarted. Where I left off was, just a couple seconds ago, as far as you're concerned, that finding the energy of each of these sort of conceptual stages of our reaction. So our first stage would just be our reactant energies. Then as the reactants move closer to each other, their electrons are going to start to physically sense each other, and that is going to be an increase in the energy. And then we're going to reach this hardest position, this really tough spot that we call the transition state of our reaction. I think that name makes perfect sense, right? You should agree there that it's perfect because this is literally where we transition from being the reactants to being the products. Okay? It's the last moment that our reactants exist and the first moment that our products exist. It's also going to be the hardest position energetically in any reaction. And so for that reason, another name for this is the activated complex, because it's associated with the activation energy. And in fact, the difference in energy between where our reactants start and achieving this transition state is the activation energy of our reaction. This same number that we had over here, that would be the height of this barrier. So you can see the higher that becomes, it's like riding on a bike, you know, getting up over that hill. The higher that hill is, the harder it's going to be to get over that. Okay? Now, once we've formed our reactants, they start to move apart from each other, and so we're going to decrease the energy, and then we reach finally our final state of our separated, completely separated products in that case. Right? Now, these don't all have to go downhill like this. There are many different versions for what this would look like. One other energy that's available on a reaction diagram like this is the enthalpy change of our reaction, something we considered back in chapter 6. So this particular case is an exothermic reaction, right? Because from where we start to where we finish, we've gone downhill as the net energy change. But look, that we didn't go straight downhill. We had to first go over this, this energy barrier. So all reaction coordinate diagrams would have these humps associated with them. So now if we consider our a reaction mechanism like we had earlier, say we had two steps in our mechanism, like we had A plus A to give us T, and then T plus B to give us C. This mechanism would give us a reaction coordinate diagram that has two steps. So perhaps it would look like this. And each step would have a an activation energy. This would be the activation energy for the first step, and then this much smaller one would be the activation energy of our second step. And this is why, if you look back in your notes, this is why I would have said the first step was slower. Okay? Now this reaction overall, from where we start to where we end, this is an example of an endothermic reaction. Okay? Now if we add a catalyst to this situation, what the catalyst would do is change the pathway. So if we added a catalyst, I won't write out a new mechanism, but it would add a third step. We still have to end at this position and start at this position, but we would never have this giant hump. So maybe we would have three equally or smaller steps to it. And if you gave me the choice of doing the black line for a bike ride or the blue line for a bike ride, I would probably choose the blue line because none of the hills are as big. Here's my first activation energy, here's my second, and here's my third. So you can see that none of these are anywhere as large as the previous case. So the blue catalyzed reaction has smaller activation energies than the uncatalyzed version of the reaction. And as such, the catalyzed reaction will be much faster. And so more molecules are going to be able to overcome these smaller energy barriers represented by the activation energies, and that's going to make for the overall faster reaction. Okay? So collision theory, to tie it all together for us again, tells us that we can't have reactions unless our molecules collide. But not every collision is successful. We need them to occur with enough energy to get over these potential energy barriers that we have. We also need them to occur in the right orientation. And we can figure out the rate constant, or how fast a reaction is going to be, if we know something about these activation energies and the frequency factor. So how often a collision is likely to occur in this correct orientation. All right? So that wraps up our chapter 13, and now we're ready to move on to chapter 14, where we're going to talk about equilibrium chemistry, so the reversibility of chemical reactions. Thanks for your time, and I'll see you in class. Take care.